Welcome to a lesson on probability, and of course we're going to say that probability rules, and that's true. You never know what's going to happen, but probability can help you find the answers as long as you remember the rules. So let's make sure we've got all the rules for calculating probability under our hat. As well as that, we want to ask some big questions about how this section of mathematics can help us in our everyday lives. So let's go and have a look at some of those questions. The first one is it possible to use maths to predict the future? Is it possible to find the chance of one or even two different events occurring? Well, fortunately, the probability rules help us with exactly that idea. It might not be able to tell us definitely what's going to happen tomorrow, but it will give us an idea of the chance of whether something can happen or won't happen on a particular date. So let's get a big picture idea by going through a concept map of all you need to know about probability. So in our concept map here, we're going to be covering certain things. We're going to be looking at the idea of theoretical probability. We're going to be looking at the idea of what is a sample space and how we can represent that sample space into different events or different sets, which we call Venn diagrams. In terms of the Venn diagram, we also introduce the word complement. We'll discuss a little bit about that. When we're considering two or maybe even more events, we have this terminology of that the events could have an intersection or they could have a union. And then there's this very interesting idea of something being called mutually exclusive. So when we have a look at this big concept map, the big overview, I hope you can see there are different parts. But what's really important is that you get the terminology and you get the ideas that come from really the most simple thing about probability. So let's get started by looking at some of these rules and some of these terms that you're going to need to become very familiar with. So the first thing that we're going to look at is the idea of a sample space. A sample space is a collection of events or outcomes in an experiment. So when we do probability calculations, we usually do experiments. And when we say all of those things, all of those outcomes or events, they're part of the sample space, we write that sample space as S. When we want to know the number of events, then we're going to write it as NS, just like that. So I hope you can see that the sample space covers many possibilities. In fact, it covers all of the things that we're looking at. But how do you think we could represent that graphically? Some people don't like the little numbers and the N brackets S. Is there a way that we can visualize what the sample space looks like? Well, absolutely there is. Let's have a look at it. And here we have, representing the sample space, we've drawn a rectangle, and inside the sample space, there could be a whole number of different events, different things taking place. And that is encompassing the things that we're examining. So within the sample space, we can now put into it things that we would like to happen, that we don't want to happen. And we could represent within the sample space a circle or a Venn diagram. A Venn diagram is represented as a circle, but it really is just a set. It could be a set of numbers, it could be a set of games, it could be a set of sports, but it's a list of things that we would put into a particular grouping. Only remember that it is part of the sample space. And so again, when we look at it, we recognize that it contains certain elements, only some, or events. And we denote it with a letter X or A or B or whatever. If we want to know the number of those events or outcomes in a set, we say it's the number N in brackets X. And to represent it graphically, there we go. We've got this is the set. It's the Venn diagram that we're looking at. The Venn diagram of those outcomes or those events that are part of the sample space. So we recognize that it is not overtaking the sample space, it's within the sample space. Now, if we go on and we say, so what's this idea of probability? How does the set, this Venn diagram of X events, the ones that we would like to happen, fit into all of the possible events that are represented in the sample space? Well, the theoretical probability is easy to calculate. All we've got to do is we've got to count the number of times a particular outcome or event takes place, and then divide it by the total number of events in the sample space. So we get this idea that the number of favorable events, the ones that we would like to happen or we're interested in happening, is divided by the total number of events. And so the probability of X taking place is simply this fraction. It's the number divided by the total number in the sample space. Just to be aware that this can be represented as a percentage, it can be represented as a fraction, and that could be a common fraction. So it could be something like 1/5, or it could be represented as a decimal fraction, or it could even be represented as a ratio, something like 1:5. All of those are possible representations of probability. And so if we recognize that, there's another key thing that I want you to recognize, and that is, what's the probability of the sample space? Well, it's the number in the sample space divided by the total number in the sample space, and that comes out to 1. Now, guys, that's a very important rule, and it's a very important conclusion that we must remember, that if something is certain, we're going to take something from the sample space and we say, what's the probability of this thing happening? Well, it has to be certain. It has to be certain because it's in the sample space. The total number of things in the sample space divided by the total number of things in the sample space, it's 1. A percentage of 1 is 100. That tells us if the probability of something happening is 100%, we know it's certain. Of course, if the probability of something happening is 0, what do you think that tells us? Well, it's never going to happen. It's like, what's the probability of, say, finding a unicorn? Well, we don't want to disappoint too many people, but we'd recognize that in terms of what we currently know, the possibility or the probability of finding a unicorn is there's no chance. Of all the animals on the earth that we know about, there's not one unicorn. So we'd have to recognize it's never going to happen. The probability is 0. So there are two extremes in probability. 0, not going to happen. Definitely going to happen, it's 1. All the other probabilities lie between 0 and 1. So we can have a probability of 0.5 or 50%. That tells you it's a 50% chance of happening or a 50% chance of not happening. It's even. But if the probability was 0.8, then it's more likely to take place. If the probability was 0.2, it's less likely to take place. I hope you've got those big ideas about what theoretical probability is about. But now we have to link to reality. Theoretical things don't always match what's happening in reality. So you might want to say, well, I'll take my probability tools and I'll go to the casino and I'll win lots of money. Well, you might not. You might have a problem because, you see, probability only works when there's a very large number of data. And if we are going to do experiments in probability and we do a number of trials, we get something called relative frequency. These come from doing games or things like tossing a coin or rolling a dice over and over and over again. And if we do that, we'll find if we do enough of them, then the relative frequency matches the probability. But you have to do thousands of them to get very close. So let's just define that relative frequency idea. So if we're doing real experiments, we recognize that the relative frequency is calculated by the number of favorable events or outcomes that we're looking for divided by the total number of trials. And a trial is just something that you're going to do. And we write it like this: it's the number of things that we're looking for divided by the total number of attempts that we're going to do it in. Here's a new word: complement of a set. The complement of a set includes all the elements of the sample space that are not in X. So the complement of X is written as X with a little dash or prime on it. So let's have a look at that visually. So in this case, we've got the sample space with X on it, the Venn diagram of X. Now look what happens. All the blue represent the elements that are not in X. They make up the complement of X. So everything in blue belongs to the set that is the complement of X. Now, we have some rules about the complement. We can say, what's the number in the complement? Well, we can say the number in the complement is the number that isn't in X. Well, what does that mean? Well, it means it's the number in the sample space minus the number in X. And if we were to look at probability, then we'd recognize the probability of the complement is going to be the probability of the sample space. Remember, it's the number in the sample space, it's the probability in the sample space minus the probability of X. And we know the probability of the sample space is 1, so we can get the probability of the complement is 1 minus the probability of X. Now, this is a very useful rule, and I want you to make sure that you've got it very clear, because we're going to show how we can use this in some applications of the rule a little later on. Let's get on to our last two rules, which are about the union and intersection. So here we go. And what we recognize is that in a union, we've got, it is the interaction that contains all the elements of the set of at least one of all the sets together. So the elements that are in at least one of the sets. And we write it as X union Y, or we say X or Y. Now, this is quite important. You recognize here we've got the purple box representing X union Y. They can be in X or in Y, and only in X or Y. When we go on, we recognize there's an intersection when they overlap, and we write it with this U formation, and they must be in both sets. Now, what's important here is if something is in the intersection, we only count it once. Even though it belongs in the particular set, like say X, and it belongs in Y, we only count it once because it's part of the intersection. When we get this, we recognize that in this case, you can see the overlap is here. The intersection is not equal to 0. But we can have a situation like this one, where the intersection, there is no overlap. The intersection is equal to 0. When this happens, we say that these events or sets are mutually exclusive. They cannot happen at the same time. The intersection is 0. And so we can represent it like that, as we've seen. And when we calculate the probability for mutually exclusive sets, we recognize the probability of X or Y happening is equal to the probability of X plus the probability of Y. We call this the OR rule. And I think that's enough of rules for the moment. We're going to investigate some more rules, but I think it's time to take a short break. Welcome back. I hope you've managed to recap all of those probability rules and terms that we've gone over. And I hope it's making some sense. I hope you remember some of those from work that you've done possibly in a previous year or in a previous lesson. So make sure that you're very familiar with these particular terms. They are very important. We ended off by talking about mutually exclusive events. We recognize those are events that do not have an intersection. For example, when you spin a coin and you toss a coin, we know that it can either land on a head or a tail. So it can't land between a head or a tail. So the number of times that it lands on heads or the number of times it lands on tails, those are mutually exclusive. It can't land on a head and a tail. There's no intersection. It can't be half of one and half of the other. And so please make sure that you understand that. But there are events that can take place when two things can be in common. So something can belong to two sets or two events that make sense, that overlap. Okay, we're going to look at such an example just now when we have a look at a particular game of rolling a dice. In fact, we're going to roll two dice, but let's get into the idea that we're talking about. So for mutually exclusive events, we recognize that the probability of P or Y is equal to the probability of X plus Y. That is for mutually exclusive. What we want to ask the question, does this hold true if the events are not mutually exclusive? We know this is true if they are mutually exclusive. If they are mutually exclusive, there's no intersection, and we recognize that we can take the probability of the individuals and add them together, and we'll get the intersection of the P, X, or Y. Okay? Please remember that when we talk about P of X or Y, we're not talking about a smaller set. We're actually talking about a bigger set. The conditions are less stringent. It isn't just P, but the element can be in P or it can be in Y. So there are more options. You've got to be very clear about this. People often think that all means it's a smaller group. It's not. It's a less of a condition. It can be P of X or in Y. So please make that very clear, particularly when we come to talk about intersection, when we're going to be using the word and. And now you might think it becomes bigger, but actually it becomes smaller. And so that's a little bit of the thing that you're going to have to get your mind around, and we'll mention it again. So, does this hold true for mutually exclusive events? Well, let's have a look at our game. So let S be the sample space of numbers on a die, and we've got two die, because we're going to have a game of rolling two die, and a die X will produce blue numbers, and die Z will produce red numbers. So let's just think about that for a minute. The red numbers on the red die, there can be 6 of them. That would be in the sample space. And in the blue numbers, there would be 6 of them. So the total number of elements in the sample space is 12. That's right, there are 12 numbers in the sample space. And we can represent that like this. In our diagram, we can see we've got numbers 1 to 6, blue, and 1 to 6 in the red zone. Now, what are the rules of the game? Remember, the game is all about winning, and there are only certain things that are going to make you a winner. Very important that you understand the rules, because you're going to take turns, and you're going to throw 2 dice, and you want to know whether you've won the round or not. So have a look at what the rules are for this particular game. The winner of a round rolls die X with a value that is greater than 2. These belong to set X. So when we think about this, not all the numbers that are part of the X are going to be winning numbers. Only some of them. They have to be greater than 2. So that means it can't be 1, it can't be 2. But if it's greater than 2, then it will be 3, 4, 5, and 6. So there are 4 numbers that will be true for making you a winner. That will be set X. There we go. We've got 3, 4, 5, and 6. Very good. I hope you understand that it's those ones that we're looking at. So we've calculated and we've seen graphically that there are 4 possibilities for winning when rolling dice X. But what about the second dice? What about dice Z? Have a look what the rules are. So in this game, dice Z, you can be a winner with a value that is less than 4. And these have to belong to set Z. So it's not the same as it was for dice X. Dice Z, the red dice, now has a different set of criteria that make you a winner. Have a look at it in the graphic form. Here we go. There's all our values. And what we recognize is that there are 3 values that you can win with slide or set Z. If you roll a 1, 3, or 2, you can be a winner with slide Z. Do you notice something? What's the total number of values that are either in set X or in set Z? That's an interesting question. Remember our OR rule. That means union. They must be either in X or Z. Let's have a look. We're going to say that we notice that there were 7 values altogether, but there's an intersection. 3 is common to both X and Z. There's only one element. So we can say immediately, we know that there's an intersection, they're not mutually exclusive. So of the 7 values, now remember what I've said, when there is an overlap, we're not going to count the red 3 and the blue 3 as separate values. No, they're intersecting, they just have one value. So we're only going to count those once. We must make sure that's true. And so when we do this, we're going to say to ourselves, in how many ways can we win rolling dice X? And what is the probability of rolling a winning number with dice X? Well, let's have a look at the picture again. So there we go. We've got the number of winning numbers, the number in X, and I think we can show X over there. We can say there are 4. The number in X is going to be 4. And what's the probability? Well, the probability of winning here is we know that there are a total of the probability of X is going to be the total of the number in X divided by the number in the sample space. And if we do that, we'll recognize that is going to be a value of 4 out of 12. Okay, let's see if we've got that. And we move on and we say to ourselves, in how many ways can you win rolling dice Z? Well, that's not that difficult. And we can count it. If we look at the Venn diagram is very useful for us to see exactly what's happening. So count with me. If we go to our slide Z or our set Z, we recognize the number in Z this time is only going to be 3 values, 1, 2, and 3. So there are 3 values. So the probability is going to be, the probability of Z is going to be the total number of z, which is 3, divided by the total number of values in the set, so we're going to get a value of 3 out of 12. Not quite the same, because you'll recognize there were more in x, less in z. Now there's a problem, because what we recognize is if we were to look at the union of those two, in other words, if it was in x or z, then what's that number going to be? Let's have a look at the question. What happens if a dice falls on 3? Does it matter which die falls on 3? No, it doesn't matter. We recognize 3 will still be a winning number. So the number of times that we can... So 3 is a winner. But we're just going to count the 3 once, because it's in the intersection. Now, if we look at how many times you can you can win rolling dice X or Z, this is what I wanted to get to. We recognize how many ways you can win in X or Z. So we recognize, Right, what's the number that we can find in the union of X union Z? Now remember, these are all the values that are going to make you a winner. So we can count all of those numbers, and we will find that there are 6 values. Because remember what we've just said, that in the intersection, we're only going to count 3 once. Because in the intersection, the 3 belongs to X and to Z. But if we're looking at the union, we're going to look at only 1 value in the intersection. So there are 6 possible ways of winning. So what's the probability? Well, it's not difficult to work out. The probability of X union Z is going to be the number of X union Z, which is 6, divided by 12. Now, if you look at that, that's an interesting result. Very interesting, because if you remember what we've calculated earlier, it kind of breaks down a little bit of a rule. But let's have a look. So if you look here, you'll recognize that we've only got 6 numbers in this union. And so that's why I've indicated this as the union of X and Z. There are 6 numbers, and you can see them very clearly. This one is in the intersection. And when we do the calculation of the probability, we have to ask ourselves then is what is that probability? And we've calculated it already. Jumped ahead a little bit. We've said that that probability is going to be 6 out of 12. But do you remember we calculated earlier that the probability of X was 4 out of 12, and the probability of Z was only 3 out of 12. So guys, that kind of doesn't add up, does it? We've got a little bit of a problem here. And so remember, this is clearly indicating that these 2 sets are not mutually exclusive. Because if they were mutually exclusive, then the OR rule would apply. We'd be able to take the probability of X plus the probability of Z, and it would add up to the probability of X or Z. But that's not the case. So let's be very clear. Is the identity for union true? And the answer is definitely no. It is not true. We've shown you the values. So what conclusions can we make? How can we make it? What is the thing that is breaking the rule here? Well, it's that idea of dealing with what's in the intersection. You see, 3 belongs to both x as well as belonging to z. And we can't count it twice. When we count the probability of x and then we count the probability of z, we're counting the 3 in both of those. And we're not taking into account that it's in the intersection. So when we have sets that are not mutually exclusive, we've actually got to take away the amount in the intersection, so to avoid the double counting. So in this respect, we can have a look and we can see that if you do that, you recognize there's only one value that's representing 2. We've got to take away the amount in the intersection. And so as I've got it here, you can recognize that this was 6 out of 12, this was 4 out of 12, this was 3 out of 12, and in the intersection we've got 1 out of 12. Now if you add these two together, you get 7 out of 12, and can you see there's 1 out of 12 here? So what happens if I subtracted that 1 out of 12? Well, then it could get to be 6 out of 12. And that's exactly what we're going to do. When we have sets that do have an overlap, that do have an intersection, where the intersection is not 0. In other words, for non-exclusive sets, non-mutually exclusive sets, sets that are not mutually exclusive, we can have this identity. And we're going to use this as our OR rule for things that are not mutually exclusive. Take a note what we do. We say it's P, the probability of x or z, is equal to the probability of P of x plus P of z minus what's in the intersection. And that, boys and girls, ladies and gentlemen, is the most important rule for calculating the OR symbol. Okay, so please remember there are 2, one for mutually exclusive and one's when the mutually exclusive rule doesn't apply. They are really the same thing, because when we have mutually exclusive, then the intersection is 0. I know that's given you a lot of food for thought. I hope you're going to practice this. And I'm going to give you the opportunity to practice all these rules. But first, let's take a quick break. Welcome back, guys. Let's make sure that we can apply the rules of probability to some practical problems. Now, one of the most common things that you will get asked in a test or an exam or even do an investigation is playing cards. But just make sure you've got all the big details of probability in front of you. So it's very important that you revise often the concept map that we've been dealing with. We're going to try and make sure all of these details are things that we can explore in our little game with the playing cards. So we're definitely going to look at theoretical probability at Venn diagrams, at 2 events, union, intersection, and whether things are mutually exclusive or not, and apply the OR rule. So here's our little situation. We've got a deck of playing cards that contains 52 cards. So there are 52 cards in this deck. They are ordered in 4 suites. Now, we have the hearts, the diamonds, the clubs, and the spades. Remember the hearts and the diamonds, these are the red cards, and the clubs and the spades are the black cards. There are 13 cards in each suite. So you've got 13 hearts, 13 diamonds, 13 clubs, and 13 spades. That all adds up to 52. The sample space in this situation is 52 cards. So please remember that. We're going to need it as we go forward to the questions. So we're told this, that one card is selected from a deck. The deck has 52 cards in it. what is the probability of selecting a red card from the deck? Guys, this is so easy. We just have to apply the rule of defining theoretical probability. Do you remember what that is? That's right. We're going to say the probability of choosing a red card from the deck is equal to the number of red cards that we've got divided by the number in the sample space. Now, if you remember, I said to you there are 4 suites, and in each suite there are 13 cards. There's a suite of hearts, which are red. There's a suite of diamonds, which are red. So 13 plus 13 tells us that there are a total of 26 red cards. So the number of red cards is 26. And the number of cards in the deck is 52. And so the probability of choosing a red card from a deck is 26 out of 52, which is 50%. It's 1 in 2. You've got a chance of either choosing a red card or a black card. The ratio would be 1 to 2. 50% probability, or we can write it as 1 over 2. That was easy, and I'm sure you've got it. I'm sure you're with it. Let's step it up a level. Let's ask our next question. So we're told that one card is selected from the deck. What is the probability the card is a heart or a face card? So what do we mean by face card? Well, a face card is something that is either a jack, a queen, or a king. It's got a face on the card. We can see what it looks like. It's one of those high value cards. So the jack counts for 10, the queen counts for 11, and the king counts for 12. Some people do it in that notation. So what are we asked here? We're asked to look at 2 conditions. We're asked to look at 2 conditions. And the first condition is that the card is a heart. So we want to know what is the number of hearts. And my heart isn't very clear there, but I'm sure that you can recognize that the number of hearts in the deck is going to be 13, because they all belong to the suite of 13. Now, if we ask the next question, what is the number of face cards? Well, that's a little bit more tricky. Remember that there's jack, queen, and king. And we recognize there are face cards for the hearts, for the diamonds, for the spades, and for the clubs. So we recognize that for each of the 3 suites, the face card, there are going to be 3 face cards times 4 suites, and that is going to give us an answer of 12. Do you notice something as we've counted those out? Are there elements that are common or not common to both of those 2 groupings? I think you can see, just by doing the counting, that there are 3 cards that are both hearts and face cards. So to make this a little bit clearer, I think it would be useful to draw a Venn diagram, just to illustrate it a little bit better. And I'm going to draw my Venn diagram up here. So in my sample space of 52 cards, I'm going to write the ones that are the hearts over here, the little hearts, and I recognize that there were 13 of those, and I recognize on my face cards, these ones were the face cards, there were 12 of those. 9 of them are individual, 3 of them belong in the intersection, and what do we recognize that we've got over here? There are 10 that are not face cards that are still hearts. Okay, so we're almost ready to do the calculation. Recognize that this situation is a situation where the 2 sets are not mutually exclusive because there's an intersection. So what are we going to do? If we are going to calculate the probability, we're going to say the probability of the the heart, and I'll just do it as H, union face card is going to be equal to, because it's not mutually exclusive, we recognize it's the probability of the heart plus the probability of the face card minus the probability of the intersection of those two. So it's the intersection of those two. So very quickly, what do we recognize? We know that we had 52 cards in total, so the probability, the number of heart cards is 13 out of 52. We know that the number of face cards was 12 out of 52, and we know that the number in the intersection is going to be 3 out of 52. And when you add all of those up, use a calculator, you will definitely find the correct probability of choosing either a face card or a heart. I hope you can see that we've applied the rules. Very quickly, I want to just summarize and recognize the key points that we've gone through. The sample space, don't forget it. Recognize that the sample space, or the probability of choosing something from the sample space is 1. Recognize what relative frequency is. The complement relationship is important. Union intersection, we've done it. And then the idea of mutually exclusive. And finally, our rules that apply to when things are not mutually exclusive. Guys, I hope you recognize all of these rules. And remember, probability rules for sure.